Hey everyone, so this is your homework review for your mid-unit review. And so you should make sure that you read over all of these terms and definitions, and that you're familiar with those, you know them really well, and then check out the example here, which I'm going to go over, and then the problems over here on the right. So you are, of course, responsible for completing the problems over here on the right. So let's make sure that you do this part right here, and I'm going to go over some examples here. So remember, a function is a function if it has only one output for each input, meaning that the x values or the input values cannot repeat. And so here, this is a function because 1, 3, 4, and 6 are each individual and unique, and they do not have a repeating x value, meaning that one x value doesn't have more than one possible y value. So there is repeated y values, which is okay in a function, but the x values here, for example, 1 repeats, so that is not a function. So over here where we have 10, -2, -6, 5, 8, -11, those are all unique x values. And so each x value has its own y value. So yes, this is a function. Whereas this one, we have -7 repeated here. And so this is not a function, because our x value could have a -7, 4 and a -7, 7. That is not a function. If you were to graph it, they would be, right, for example, at -7, 4, they would have two different y values for that same x value, and so that is not a function. All right, the next piece, this is our function notation, so you write f of x. And remember, this f of x is the output. So in our normal equation world, this would be y equals, right? This whole thing, f of x equals y. Remember that it is not multiplication. It is just notation, meaning it is just the way that we write a function in math world. So if a dog's weight in pounds is represented by W of t as a function of time in weeks, what does W of 8 equals 16 mean? So a function of time means that the input is time. So this is at 8 weeks, the puppy weighs 16 pounds. So here, if the function W represents the amount of water in inches that has fallen 8 hours, how would you write in function notation that 2.3 inches fell in 6 hours? So we would write this as W of H, right? And in this case, we're replacing the H with the hours. So water of 6 hours equals 2.3 inches. Again, the input being time, because it is almost always a function of time, and then that output being the thing that we're measuring that's changing as a result over a period of time. All right, the vertical intercept is on your y-axis, and the horizontal intercept is your x-axis. Generally, the vertical intercept is when your time is at 0, so that's your starting point, and your horizontal intercept or your x-intercept is whenever that thing is at 0. So in this case, the number of deer that we're counting, or it could be water in the example above, or it could be the height of something, right? If it's at 0, it's on the ground. The vertical intercept here represents the starting number of deer. So this point right here, just under 80, the deer population would be the starting number of deer. And then the horizontal intercept here is the time at which, so this tells us when the number of deer went down to 0. So between 4 and 6 years, maybe like 5 3/4 years, between 5 and 6 years actually is more accurate, the number of deer went down to 0. This graph shows Andre's distance from home as a function of time. What does the vertical intercept represent? So here is his starting distance from home. And the possible explanation could be that he's at the store or at school or somewhere else, right? What does the horizontal intercept? So that's here. So this is his distance from home. So when it's down here at 0, that means he's 0 feet or 0 meters away from home. And so the time at which he's home, or 0 meters away from home, or 0 feet, which doesn't even tell us here. Okay. Now on your quiz tomorrow, you're going to see something similar to this where you see a graph of sorts, right? And it's going to ask you which of these things are true. So as an example, it might be asking you at what time are these 2 points equal. So it might say, for example, f of 2 equals f of 10. Is that true or not? And so you're looking to see, is that height across for where the input is 2 and the input is 10? Where is that the same? Okay, you might also see things like f of 3 is greater than f of 6. And so here we're looking at when the input is 3, let's say it's here, and the output then would be at this point. If f of 6 is here, if 6 is here, and this is our output, would this f of 3 be greater than f of 6? Well, no, f of 6 here is higher than this, so that would be false. So there's a number of things that you have to go through and decide if they are true or false. It is important that you go through each one. But the main thing here is that you know these are the inputs. So you're looking to see at what time is the distance the same, right? Here, the distance hasn't changed, so what does that tell us, right? Being able to interpret that graph. All right, the maximum is the highest point of the function. Sometimes this is the same as the vertical intercept. So for example, actually that's not on one of these, but in the example of the bungee jumper that's jumping from a very tall point, and they bounce down and then they come back up, they never go fully all the way back up. And so the maximum height is that height that they start at. The maximum in this example above is approximately 4,135. And so at 4 years, that was when the greatest amount of population of deer was at approximately 135. The maximum here is actually in multiple points, but from a given time to a given time. So there's a range. So from, let's say, a little bit after and a little bit after the starting point to before the end point, there's a period of time which the distance is greater. In this case, we don't have actual numbers here, so we can't list a number. But, you know, if, for example, this was telling us 6 miles or something, right, then it would be at 6 miles between this period of time here. It's at its greatest point. The minimum is the lowest point of the function. So sometimes this is the same as the horizontal intercept and or the vertical intercept. If the starting point is 0, 0, that could be the minimum. And so the minimum in this example with the deer is at around a little bit after 5.5 years, we're a 0 deer, right? In this example, it's at a given time, right? At the end, he returns home. So let's say it's 5 minutes, 0. I don't really know because we don't have actual units here. But it is when he is home, right? Again, 0 meters from home. All right. If we're given this function of f of x, then we can solve for f of x by substituting in x, right? And then the opposite, if we are given f of x, then we solve for x. All right, so if we have x, we plug it in. If we have f of x, we plug that in for y and solve for the input. So here's an example. Miss Lee buys 60 pounds of clay for her earring making. I do actually make earrings. She uses 2.5 pounds of clay per week. If the remaining clay is a function of time and weeks, write a function to represent this. So here's the function. This is my starting amount of clay, and then every week I use 2.5 pounds. So I'm subtracting 2.5 pounds per week. Right after 1 week, then I would have 2.5 pounds less. After 2 weeks, I would have 5 pounds less. 7.5, and so on and so forth, okay? So as the weeks change. This should actually be either C of x or a W here. That's confusing. I apologize for that. And so this is a graph of my function. It says how much clay will be left after 5 weeks. So if I know the weeks, that's the input, I can plug that in here and subtract from 60, and so I know I would have 47.5. So let's look at this. I have 35 kilograms of dirt for my plants, and I use 1.5 kilograms a week. So write a function to represent this scenario. So we have dirt is a function of weeks, and I start with 35 kilograms minus 1.5 times the number of weeks. So that's my function. And then I'm going to sketch a graph. So you can just make a nice loose graph of this, right? You know you're starting at 35 and you're moving down every week 1.5, right? So we know that we're going down at a constant rate of 1.5. It's just a general graph. How much dirt will be left after 3 weeks, right? Now, if I were to actually go and graph this down, this right here shows you your slope. So this means I'm going down 1.5 over 1, or 1.5, as you may know, is 3 over 2. This is negative, that's why my slope's going down. So down 3 over 2, down 3 over 2. You can write it as such, and that can help you to graph. But it says how much dirt will be left after 3 weeks. So after 3 weeks, I'm going to fill in 3 for my weeks equals 35 minus 1.5 times 3. And so when you calculate this, it'll tell you how much dirt is left after 3 weeks. So we would be doing 35 minus, that would be minus 4.5, which is going to be 30.5 kilograms of dirt will be left. So in this scenario now, we're being given f of x or y, and so we're going to solve for the input. All right, so in this scenario, this time they told us C of W equals 10, so I'm going to plug in 10 here and solve for the number of weeks. So if this scenario says if D of W equals 3, right, that means I have 3 kilograms left, right? And so I would put this in my equation. 3 equals 35 minus 1.5 W. Now I have the output, so I'm solving for the input. All right, and so I'm going to start by subtracting 35 from both sides. I'll get negative 32 equals negative 1.5 W. Divide both sides by negative 1.5. And I know that that's right because I should end up with a positive answer for a number of weeks. I can't have negative weeks. So if you do 32 divided by 1.5, you'll get approximately weeks are going to be 21.33, which means it'll take me somewhere between 21 and 22 weeks to get to this 3 kilograms of clay left. That's a lot of clay, by the way. All right, let's take a look at the last one. So the last one is that average rate of change piece that we've talked about. And remember, this is your second y value, your second output, your later output, minus your earlier input over your later input minus your earlier input. All right, so we have a special question. I do want you to answer this. If the average population growth is 0.15 million people per year, and the population is currently 1.5 million in the year 2022, in what year will the population reach 2 million? All right. So if the average is 0.15 million, that's what it equals. And we're currently at 1.5 million. That's our, that's our output. That's how many we have. When will it reach 2 million? So when it's 2 million minus 1.5, and then we are looking at in the year 2022, what year will that be? So x minus 2022. Okay, how can we get to this? All right, that's what it's asking you. What year will that happen in? Okay, so you can then calculate, we would end up with 0.5 over x minus 2022 equals 0.15. Now to get this out of the denominator, I can multiply both sides by x minus 2022 because this is division. So we'd have 0.5 equals 0.15 times x minus 2022. All right, and then I can go ahead and divide by this. Let's go ahead and get rid of that. So 15 divided by 0.15 gives us 100. So 100 equals x minus 2022. Add 2022 to both sides. And so this means x will equal 2122. So it's going to take 100 years. If we're growing at 0.15 million people per year, it's going to take us 100 years to get to a population of 2 million from a population of 1.5. All right, so again, this is kind of a special challenge question, but it's showing you how you would set that up right? I replaced my outputs here. That's the people, the later output minus the earlier output. The later year that we're looking for in this case minus the year that it is currently equals my growth rate, and then working backwards from there. All right, let's look at this example with the table. So this represents the population of 2 cities in the thousands. What is the average rate of change from 2002 to 2007 in P1, in population 1 or city 1? So here I'm looking at from 2002 to 2007, and that's a difference of 5 years. So in my denominator, remember, because I'm putting my inputs in the denominator, it's per year, so years goes in the denominator. And then I did 52 minus 42, right? Because my output, that's how many people were there. So that's how you can solve, and it ends up being 10 minus 10 divided by 2, or sorry, 10 divided by 5, which is 2, when that is 2,000 per year. It says which city had the greatest average rate of change? And so the average rate of change is from this year to the end year. Well, 2019 minus 2002 is 17 years. So I'm putting 17 years per year in the bottom. And then in the top, it's the thousands of people. So 76 minus 42 for this first population, the city. And then 65 minus 82 in the second population. Now notice that one went up and the other went down. But overall, the greatest change here is this one because it's greater. Even the absolute value of that is greater. All right, let's look at this one. It says, which is greater, U of 1970 or R of 1970? Okay, so let me see. If I should have made this much bigger, I apologize. I'm trying to make this bigger for us now as we look at this. Okay, so U is the red line and R is the green line, right? So U of 1970, if we look here, we have 1970 is right here, okay? So in this case, the rural population in 1970 was greater than the urban population. So R of 1970 is greater. Was there ever a time when the population was equal? Yes, the population was equal here sometime between 2000 and 2010. We can probably estimate around maybe 2004 or 2003. Kind of hard to tell there. But yes, it was, and that's where they intersect right here, because at this time, their population is about 3.25 billion approximately. So when those lines intersect, it's showing us that they have the same output. Okay, so I'm going to review this one more time. The average rate of change is the same as the slope. It is the later output. I'm just writing it at this as this to help you all out. The later output minus the earlier output divided by the later input minus the earlier input. And if you can't remember which goes where, remember that almost always we are looking at functions of time. So miles per hour, or, words per minute. And so usually your time is going in the denominator because it's per that time, right? So for example, miles per year. Well, that's miles per hour, okay? In this case, it's population per year. And so that per tells us that the other thing is going in the denominator. The time is going in the denominator. So again, because functions are almost always a function of time, they are almost always your time, minutes, hours, years, measurements of time are going to be in the denominator. So hopefully that is helpful for you. Okay. I'll go ahead and give you a code word on this so you can get extra credit here. So just write your code word. And your code word will be earrings, because I told you about the clay making and the earrings and whatever. And if you're curious, here is a really cute earring example that I made for springtime last year. Okay. Please reach out if you have any questions about this practice.